So I guess just a bit about me. So I'm Jeffrey. I'm I was a high school senior. I'm entering college now, and I'm a big computer vision geek. That's what I've been doing in tech for all my high school career, and I'm really excited to be sharing what I know with y'all today. So let's start with the basics first, and that's what is computer vision. And essentially, computer vision is the field that deals with how we can allow computers to gain high-level understanding from images or videos. What high-level understanding means is it ranges. For instance, this photo over here is an example of what's called semantic segmentation. So basically, this is when you take an image and basically every single pixel on it, you identify what that belongs to. So all the pixels colored in orange are considered to be part of a building. In the red, those are vehicles. And obviously, this is really useful for understanding the world. And why computer vision is really useful and why a lot of the advances today, and especially machine learning and AI, have actually stemmed from the computer vision field. Because as I'll discuss later, essentially this problem of how do we allow computers to understand the world like we do has been something that has plagued computer scientists for a pretty long time. And the field of computer vision is trying to unlock kind of this entire rich world of visuals and allowing computers to understand and automate and create processes based on it. So I'm going to start first with what's known as classical computer vision. And that's essentially using human-defined features to identify and understand images. So you may be wondering now, well, like, what do you mean by human-defined features? And, well, what even is a feature? So let's just start with a basic example. So let's just say I want to find rectangles in an image. So us humans, we could just look at that and, that's a blue rectangle right there. But to a computer, all it sees is really a bunch of pixels. So how do we really convey across what defines what a rectangle is? It sounds like something that's really simple, but it indeed is just what we need to do to allow a computer to understand it. Because after all, computers function really well when you have rules for them, and they can just simply follow the rules, and they do exceedingly well in these sorts of environments. So for instance, we can define a rectangle as 4 perpendicular edges. And that's an example of what's known as a feature. So for instance, like these sorts of things like edges and corners are really important for computer vision, because these are sort of kind of these clues for the computer to recognize things. Like, for instance, if it's a rectangle, if I'm a computer and I'm able to detect 4 edges, and then I see, hey, they're perpendicular to each other, then I know I've got a rectangle there. And that's starting from these sorts of fundamentals. That's how we can really build these sorts of complex computer vision models. So I'm just going to start there with the stop there for a bit for the fundamentals. Are there any questions so far? And just feel free to drop questions in the chat whenever, and I'll try to get to them whenever I can. So next, I'm going to discuss just the computer vision pipeline, which is essentially how, if you have a computer vision project, what's this workflow really like? And the way that the workflow works is it starts, you start with input data always. So that's image or video data that's taken in as input from the user, whether that's the user for an app or it's some internal pipeline. You're getting images and video data from somewhere, and you want to process that. So the second step is known as pre-processing. And essentially what that does is it cleans your input data through steps like noise removal. For instance, if photos are, not all photos in the world are perfect. Sometimes, it can be raining outside, it could be blurry, there could be fog. Maybe the person had really shaky hands when he's taking the photo, and as a result, there's not that many details. So pre-processing algorithms essentially try to take these imperfect images and try to smooth them out and try to get something useful out of them. And then the final step of computer vision is feature extraction. where we find the specific features in the input, and from parsing out these features, we're able to thus have a high level understanding of what this image is, and we can do all sorts of tasks with this knowledge. So let's start with what's an image. You may be rolling your eyes at me right now, but it's a genuine question. What actually is an image? To the human eye, we obviously see images every day. That's something that a lot of us take really for granted. But for computers, an image is an array of pixel values. Each image is essentially this large matrix, and each pixel has a numerical value, which is essentially the bright. For these grayscale images, it's the brightness value. So these range from 0 to 255, and you see for these darker pixels, they may only have a value of 1. For lighter pixels, they may have a value of 200 or higher. And pixels are described using what are known as color modes, which are systems for describing a full range of colors with just the primary colors. So the classical one that a lot of us know is RGB, where basically just from mixing combinations and intensities of red, blue, and green, we are able to get any sort of color that we want. And essentially, thus, we can consider an image as a three-dimensional matrix of integers from 0 to 255. We have this large grid that comprises the image. And for each pixel, we have 3 numbers from 0 to 255, a red value, a green value, and a blue value. So now that we understand that, let's get into image preprocessing, which is removing noise from raw image data. Feel free to stop me if you have any questions for the previous section. Otherwise, I'll just keep moving forward. So firstly, what is image noise? So image noise is random variation in the image data that obscures the desired information. So if you've ever taken a photo in really low light conditions, or it's dark outside, and for some reason you decide to take a selfie, you realize that you usually end up with these really grainy photos, and that's because there's a lot of shadow, and as a result, when the camera sensor is trying to compensate for that shadow, it leaves behind a lot of this fuzzy noise, and that's not really great when we're trying to parse out features in an image, because there's all this haze everywhere. There's all these random variations in the pixel values, and it doesn't allow for really nice, neat features like edges or corners to really stand out. So image preprocessing allows us to remove noise to aid feature recognition. So I'm just going to briefly go through 3 main categories of preprocessing transforms, known as blurring, thresholding, and image gradients. So firstly is image blurring. And the question would be, why do you want to blur an image? Generally, when you get images, you want the most crystal clear, crisp images you have. So usually people are asked, like, why do you want to blur images in computer vision? But if we go back to images like this, where there's a lot of noise, as you can see in the top left corner, and there's all this fuzz, it turns out that when you blur images, that actually does really well to reducing noise. The other images, for instance, are actually blurred versions of that same original image, because what blurring does is it essentially smooths out these, you can think of like these dots of noise as almost like spikes in the pixel values. And we don't really want that, because it's like a rough matrix. It's really messy. And instead, when we blur things, we are able to smooth out these values, and it actually results in us being able to detect things like the real edges and the real corners a lot easier. So there are several ways that you can blur an image. So the most common of which is known as Gaussian blurring. So essentially, you take what's known as a kernel. And a kernel is simply just a small, usually square or rectangular region over the image. And you can think of it as kind of like a small net. So you start with, so you look at the pixels in a certain neighborhood and you take in their values. And based on that, you will adjust the values of a pixel based on the values of its neighbors. So in a Gaussian kernel, for instance, you can see examples of different kernels here. So for A, that's an example of just a normal kernel, where basically, if I'm a pixel and I want to kind of recompute my value based on the values of my surroundings, so that way I'm blurring it, because the idea behind blurring is, after all, generally one pixel will be pretty similar to pixels in its neighborhood. So for A, this is generally, these values are of equal weight. So it's usually 1, 1, 1, 1, 1. And you can see there's these other kinds of kernels though. Gaussian kernels, basically you weight pixels that are closer to you. After all, the idea behind that is that if there's pixels that are closer to me might be more similar to me. So thus, when I am recomputing my pixel value, I want to weight kind of my neighbors more than those pixels that are further away from me. And essentially how this Gaussian blurring works is I take, if you can look at the bottom image, for each pixel, I look at the surrounding pixels values, and then I multiply all these values with this kernel that these kernels are pre-computed, and people have found that like these sorts of kernels like up there have been really useful for this sort of blurring. And you multiply for each pixel value, you multiply the corresponding kernel value, and then you add all the values together, and that will be your new pixel value for the center pixel. So kind of a TLDR of that is image blurring. You basically take all your neighbors and kind of sort of take like a weighted sum of your neighbors and then recompute your pixel value based on that. That was a pretty lengthy explanation. So just, does anyone have any questions about that? Just feel free to drop them in the chat if you do. All going once, going twice. All right. So next is image thresholding. So this is really useful if you want to detect kind of the difference between the foreground and the background, or if you want to really make out edges. So a thresholding operation sets an image's pixel values to either 0 or 255. So it's either black or white, based on whether the current pixel value is above or below a certain threshold. So in this example, we have this grayscale image of a photographer. And really, if we just want to extract all the edges, like for instance, his elbow, what I can do is I can simply say, for all the darker values, I just set them straight to 0. For all the lighter values, I set them straight to 255. So that way there's a lot more contrast, and that makes it really easy to tell where edges are, because edges are just the regions where there's a large change in the pixel value. And finally are image gradients. So image gradients are useful because essentially in calculus, like gradients are basically like an indication of like the direction of greatest change. So that's useful because like if you think about what an edge really is, it's when there's a lot of contrast between, like say if I have an edge right here, like perhaps like the pixel values above this edge are a lot brighter than the pixel values below this edge. And it's like this it's this great contrast between the values in one region versus the values in another region that really make up, what an edge is. If you think about it, the same thing with a corner, which is just a corner point could just be, one specific region is a lot more intense than other regions. So that's why image gradients are useful. And essentially what you can do is, it's a bit of calculus, but you can take the gradient in the you can take the gradient in the x direction and then the gradient in the y direction, and then you can combine them with some math. And basically, what you can get is you can take this, for example, this example image of an alpaca, and the output gradient image is on the right. And as you can see, all these edges really stand out because we're calculating these intensity gradients, and you can sort of see like these directions where the pixel values are changing the most, which can be really useful. So that sums it up for image preprocessing. So are there any questions so far? Oh yeah, Leo. Yeah, image gradients are kind of painful to do, but we'll get to how to implement these after the slideshow. So stay tuned. There's a Google collab. Anyway, cool. And Melinda, yeah, Leo's recording. So I think it'll be on YouTube later.
Yep, all workshops are uploaded to our YouTube channel.
All right, cool. So next, I'll be discussing feature recognition, which is the meat of how you're really going to extract useful information from an image. So the first is edge detection. I've already talked about why you want to really detect edges in an image before, because that's when you can tell like kind of foreground from background. That's how you can really identify what objects are. And the most famous one of these algorithms is the canny edge detection algorithm. And it's a three-step process. So on the left, you can see a before, and then on the after, you can see an after. And you can see it does a remarkably good job of parsing out the individual edges. Like you can see in the right-hand edge image that like the individual strands of hair are delineated, which shows like how powerful this algorithm really is. So there's this three-step process, which is first finding the intensity gradients. Second, the step known as non-maximum suppression. And then finally, the algorithm does some sort of thresholding. So again, we discussed what intensity gradients are and why they're really useful. So we just discussed that. So that's basically the first step. You find the gradients, you find the areas where the pixel values change the most, and you mark those out. But oftentimes there can be, there's sometimes noise, there's sometimes regions that just have a great deal of change, but might not be a part of an edge or anything. So the next step is non-maximum suppression. So in non-maximum suppression, we check the orientation of each pixel. Basically, if there's a direction of change, like what's the greatest direction of change there is. And then we look at the neighboring pixels. And if it's the most intense pixel in that neighborhood, then we keep it. Otherwise, we throw it away. And like you can see an example in the bottom image. So we start out with this edge and it's sort of thick. And we see there's some like really intense pixel values in the middle. But then you see some like kind of on like the sides of the edge that like there's still like this direction of change and it's still like part of the edge, but it's not like the strongest part of the edge. So what we can do is we apply non-maximum suppression. So we only pick so you see if we look at the end result here on the rightmost image, we only pick the strongest, most intense pixel values that make up that edge. So that way we don't have kind of like these extra pixels that we don't really want to deal with. And then finally, we set up two thresholds actually for canny edge detection. So there's what's known as a strong threshold and a weak threshold. So any pixel values that are greater than the strong threshold, we just say they are for sure, they're part of an edge. If any pixels are lower than the weak threshold, we just throw them out. We just say there's no way they're an edge pixel. If they're in between, if one of their neighbors is a strong edge pixel, we keep them, otherwise we don't. So this sort of thresholding keeps, I don't have a good example photo of this, but this sort of thresholding essentially also does this sort of edge thinning where only like these pixels that we picked out in the last step, if a pixel is directly neighbored to these strong pixels, they'll stay, but otherwise we throw them out. And that's just so we can thin out the edges. And that's why, and we're able to get really clear, like delineated edges, like in this result image. If we didn't apply these steps like non-maximum suppression and thresholding, there could be like a lot more pixels in here. And for instance, this region of the hair could just all be white, which is not really useful when we want to mark out the individual edges. So again, that was a lot, but all right, I see there's things in the chat. Oh yeah, reminder and if there's any questions right now, feel free to drop them in the chat, or if you want to say anything. All right, cool. You're smart getting all this. So next, I want to talk about Harris corner detection. So corners are the other major feature that I discussed that are really useful. Like after all, like detecting corners are like, it's similar to detecting edges in that that's how we can identify like maybe like that there's an object there. And this is another super famous algorithm, the Harris corner detection algorithm. And essentially the way it works is you detect points with strong changes in intensity from all directions. So again, you're going to be using an image gradient. And the reason why we want it from all detections is like definitionally, that's kind of what like a corner point is. Whereas for an edge, there's a strong change in one direction. It's when you're going across the edge. A point is like a point sticks out because it's different from all the pixels around it. And so that's why we care about the gradient image again, and we want a strong change in intensity from all directions. And then there's some linear algebra that I'm not going to get into because, quite frankly, I doubt you care about the math behind it. And you basically can extract eigenvalues from. If you don't know what those are, don't worry about it. Honestly, I don't know all the math behind it's some of the like most advanced like computer vision algorithms. It's a very math heavy field, so no worries if you don't get it. But basically, again, you calculate the change in intensity by creating a gradient image, and then you can do some matrix calculations to define whether it's a corner or not. If they're certain, based on these eigenvalues, you can figure out whether it's a corner, whether it's an edge, or whether it's just a flat region. Questions? So if you conceptually want to understand a lot of computer vision, like linear algebra is like pretty key, and also calculus as well. It's like that's why like honestly, like if you get into game design and you're doing things like ray tracing and like computer graphics, like the amount of math that goes behind it's actually insane. Like I remember when I was starting to learn computer vision and I was like really clueless about like the math behind it, and I was trying to find a place to learn. And it turns out that the place like I learned the most from wasn't, some you'd expect I'd learn, linear algebra or something from some like really dry textbook or like some like college course online. But I found that like if you go onto like game development forums where people are doing like graphics and like ray tracing and stuff, like you can low-key learn a lot of you can low-key learn a lot of advanced math like there. So anyway, funny thing about that. And not to like scare you guys though, like in practice, if you want to implement this, you definitely don't need to know all the math behind it. But if you decide to become a massive computer vision geek and you want to get a PhD in computer vision or something, and you really want to understand, the nitty gritty, like why do these algorithms work the way they do? Definitely a strong foundation in math is important. But if it's just something you want to apply to like an app or a project you're working on, you don't need to understand all of this for sure. There's plenty of times where I'll unabashedly say I have no idea like about the math behind some of these algorithms, but they're still really useful. So yeah. Questions? Yep, Leo knows what's up. Anyway, now let's transition from classical computer vision to machine learning methods for computer vision. And I guess the first reason is because it's hip and cool. It's what everyone cool is doing today. But it's also computer vision and machine learning have been pretty intimately tied since the start. So I think it's important that we understand why like ML in particular advantages have stood out in the computer vision field. So firstly, what's ML and like or AI broadly. Um, and like definitionally, it's a field of computer science devoted to formulating algorithms that allow machines to modify and learn behaviors rather than sticking to explicitly programmed guidelines. So so before like when I said, oh, like computers are really good at following rules and just sticking to that, well, like that's a lie now because machine learning is now a thing and computers are able to learn. And the reason, and like a common question is like, why do we care about this? Like, what's cool about computers, like being able to learn? And that's when computer vision actually serves as a really good example of why machine learning is like this revolutionary new thing in computer science. So here we have three photos of cats. You can look at them immediately, and we can, as humans, we can just see like, yeah, those are cats. But if you think about it, all three of these images, if you think of it from a computer's perspective, these are three completely different images. So like, for instance, you have a tabby cat here, you have an orange cat here. This cat doesn't even have like its body showing, it's just half of the face. And, like if we want to go back and like think about, oh, how do I define like a rectangle? Like, sure, that's easy because I can say it's four perpendicular edges, but how do you define what makes up a cat? It's like it's different every time. It's the color of the fur is different. Sometimes the angle is different, right? Like in this rightmost photo versus the leftmost photo. Like if it's just showing part of its face, you can't even say it's two ears. You can't even see the paws. Like this is tricky. And if you want to go and manually program out like each rule and say, oh, if I'm able to detect, these edges at this angle, and if I find these corners in these certain places, then maybe it's a cat. That might work for one image, but are you going to be able to make sure it works for like every single image out there, like all the different poses that cats can make? So for a while, that's why computer vision and like image classification in particular was really tricky for a lot of computer scientists, because it was a lot of people trying to find ways to recognize these human defined features, but ultimately the features were human defined. Like humans were the ones that said, yeah, like ears are an important part of like what a cat is. I want to look for ears. But then, what if a cat's not showing its ears? Then like you're kind of screwed. So machine learning's come along and basically thrown that all out the window. Basically, us humans, we don't have to define what features the computer needs to look for. We just give it a lot of training data, and the computer will learn for itself what features it finds is the most useful for classifying these images of cats. And this change in mindset has completely revolutionized the field of machine learning, of computer vision. So back in 2011, using classical techniques, at best, like on the famous ImageNet, it's basically this, it's a pretty well-known image recognition task in the computer vision community. Top accuracy was 50%. And that was only for the top 5 classes. So that was just out of 1,000 classes, if you could get in the top 5 of what the thing was. And they could only do it 50% of the time. Wait, just kidding. It's top 1. I don't know how to read my own slides. But now, like this year, we're up to 90% accuracy. That's human level performance when it comes to the ImageNet recognition task. So computers now are seeing just as accurately as we are, which is insane to think about. Just over a 10-year gap, we've gone from like computers can't recognize anything to computers can see as well as we do. So I just want to go over now the pipeline for how a computer vision project would work in a deep learning or AI sort of framework. So the first is training data. That's really important. Okay, I see a question in the chat. Again, yeah, I hope I'm not speeding through these slides too quickly, but just make sure to drop questions in the chat. I'll stop and answer them because, yeah. And as for the question, yeah, will computers be able to accurately recognize things more than us humans? In some cases, the answer is already yes. There's some cases where I know in, like, for instance, in medical applications, increasingly like AI, like machine learning models are being used to read things like X-ray scans, and they're up to human performance. Obviously, like regulatory approval and all this stuff for like things like medical fields are really like, it takes a long time to get approval for stuff like that. So you're not gonna be seeing robot doctors anytime soon. But it goes to show that there's some cases where computers are already recognizing things more than us humans. Certainly, however, there's also a lot of limitations with machine learning still. In cases where you don't have a lot of data, for instance, computers are really bad at recognizing it. I guess the main bottleneck is still that if you show me, like, for instance, like, I don't know, if I'd never seen a plane before in my life and you took me to the airport and said, that's a plane. Most likely next time when I saw a plane, I could point that out. Oh, that's a plane, just from that one memory. For a computer, you'd still need probably hundreds, if not thousands of images of planes at different angles, different lighting conditions, all that stuff before you could reach the same performance. So I guess to summarize my answer is that computers can more accurately see than like us humans in some cases, but there's still severe limitations to the way that they do learn how to see. And that's something that researchers are continuing to work on. So anyway, speaking of training data, that's the most important part, I'd argue, of the deep learning pipeline. Like a lot of things are just garbage in, garbage out. Like if you have bad data, you're gonna have a bad model because it's not gonna be able to learn anything. So if you're working on a machine learning task, it's really important to get good images. So ideally images that don't have a lot of noise, they aren't blurry. There's good lighting conditions, stuff like that. But there's also have some diversity in your training data as well. You want your model to be sort of sometimes like able to adjust to these sorts of real world conditions. So increasingly people are actually doing things like adding noise and blur. So like when someone posts a blurry photo, your model will be able to handle it. So the next is model architecture, which is essentially the kind of like how you build your AI. And that's something I'll get into later, just like what specific layers, kind of like the individual building blocks of the AI that are effective, and how do you combine them to create a really powerful model that can learn well. Next are hyperparameters, which are I'll also get into later. Essentially, hyperparameters are these sorts of parameters that affect your model's performance, and those are not things that your model learns. It's things that like the human sets for like the training process and mostly the training process, but these are really important for how well your model performs, and that's something I'll get into later, how to pick really good hyperparameters, some tips for that. And then finally is like deployment, which is just, you have this cool trained model, you got to bring it to your app or, your website so people can actually use it. And question, if you look up a picture of something, say a cat, and the computer responds with pictures of cats, would that be an example of recognizing? Yeah, that's actually a field, and that's actually kind of a task in computer vision that people have been working on. I'm not going to go over it in this presentation, but it's known as have you all ever used like Google and there's like a reverse image? Like firstly, there's reverse image search, but secondly, there's also like if you're looking up something in Google Images and you click on an image and then you scroll down and there's this whole list of images maybe like similar to this one or like related to that. That's an example of kind of just like this AI being able to understand like, oh, these images are similar because they have some sort of similar features that I've like learned through my training process. So yeah, that's an example of like computer recognition. Another thing that people are working on is generative models. So like if I give like a computer a bunch of photos of cats, and like the computer is able to create its own images of cats that like look really lifelike. That's something that is like pretty controversial now because like deep fakes especially have now become like a really big concern, because it's really difficult for the human eye to tell, is that a real photo of like ex-politician doing whatever? And like there's obviously like problematic applications of that, but it's like overall, it's like something that researchers are still working on. Any other questions? Cool. So first is model optimization. Oh yeah, this person does not exist is a really cool website. Y'all should check it out. But maybe not during my presentation because I'd like y'all to pay attention. But yeah, it's a cool website. Like each time you refresh it, it'll generate a completely new photo of like they look really lifelike, but they're not real people. They're just generated. Model optimization. So the question is just, how does an ML model actually learn? And essentially, you can think of it as if y'all have y'all ever done, like lines of best fit in school and like other sorts of regression. Basically, you have a bunch of points. And based on these points, I want to kind of just fit a line through it. And using this line, hopefully I'm able to make some sort of predictions. Um, it's simple as that. ML models do this with a lot more data, a lot more dimensions, and far more complicated functions than just a straight line. But the core concept is the same. Um, in this case, like generally, we want to minimize the distance between this line, which is kind of like the prediction, or in cases of classification, it's kind of like the boundary between, like for instance, if the points on above the line are cats and the points below represent like photos of dogs or something. I want my line to kind of be a separator so that way I'm able to just say, oh, if I get a new point, I can say, oh, that's a photo of a cat or that's a photo of a dog. And the way we do this is through calculus. Yep, there's a lot of math when it comes to machine learning and also computer vision. Don't worry if you don't understand it, but if you want to get more into it, certainly would recommend learning some calculus just to understand what's going on behind the scenes. But you can totally get away, again, with not really understanding any of the math and just programming your own. So the first step of optimizing a model and allowing it to train is formulating what's known as a cost function. So basically what that does is we can take the distance between each point and the line as an example of the cost function. For instance, if I'm trying to fit this line to the data, like if my line is, going negative, that's my line's not following the data at all, right? So that would be a case where the distance between each point and the line would be really great. So that's, I can tell my model like, you're doing a bad job. Whereas, if miraculously my model is able to fit through every single point perfectly, then the distance is 0. And then, that's a good metric of that I've fit the data. Then the second is taking what's known as the gradient of the cost function. So I've talked a lot about gradients, but essentially the gradient is the direction that causes the greatest change in like the values of a certain function or point. So in this case, we want to reduce the cost as much as possible because the cost is bad. The cost is essentially how poorly my model is doing right now. So at each point, what I can do is using some calculus, I can find the direction that causes the greatest reduction in my error. And then I want to move in that direction. I don't want to move too much though. That gets into hyperparameters later. But I want to kind of take a small step in that direction. So like you can see this photo on the right side of kind of like what gradient descent would look like. So let's just say like these blue regions are like bad because they're high up. The cost is really, that represents, my cost is really high, my error is really high. And I really want to get to these red regions where the cost is low, the error is low. That means my model is doing well, sunshine and rainbows. So what I can do is essentially at each point, I find the direction of greatest reduction, and then I take a small step in that direction. I don't want to go too far because, for instance, if I'm on the leftmost corner and I take this massive step, then I go to the rightmost corner. I just went from like the peak to the other peak. I want to go into the valley. So how big of a step you actually take is something that you pick. That's something you have to manually pick. It's known as a hyperparameter. But essentially, if you let this run, ideally, your model should be able to reach one of these sorts of valleys where you have a really low cost, you have a really low error, and that's an indication that your model is doing well. So we rinse and repeat. That was a lengthy explanation. Feel free to ask any questions. You can totally tell me like, Jeffrey, I have no idea what you just said. Can you go over the slide again? That's cool. Just let me know if you have any questions, but if you're all set, we can move on. All right, cool. Now let's get into some specific neural networks and like AI models that are really useful for computer vision. So the big thing with ML is convolutional neural networks. Those are kind of the backbone of this massive improvement, why computers are able to see as well as humans now in some cases, all because of convolutional neural networks. So firstly, what is a neural network? Like, I didn't even explain what a neural network is. Why am I going on about convolutional neural networks? So essentially, a neural network is a series of interconnected artificial neurons. Basically, the inspiration is the human brain. The human brain is made up of a lot of these neurons where all they do is basically they fire or they don't fire. They have, they activate based on certain inputs from other neurons, but simply like they just fire or they don't fire. And somehow this network of a bunch of really simple functions, just do I fire, do I not fire, is able to do, everything the human brain does. So basically, researchers took biological inspiration and created these artificial neural networks, which computationally do the same thing. You have these input neurons that take in, for instance, an input image, and then it extracts some features. It does some mathematical computation and through mathematical function, and it spits out this weighted sum, and it passes it to this activation function. And if the value is great enough, then my neuron will fire, and I'll pass in an output. If it's not great enough, it won't fire. And then I pass it along, and then eventually at the output, I spit out some number. Generally, for image classification, you spit out probabilities. So like, what's the probability that this is a cat versus the probability that this is a dog versus like the probability that this is a car. Does that make sense? All right. Cool. So now that I've explained what a neural network is, I can explain what a convolution is. So you already saw this before when I was explaining what kernels are. But basically, it's a mathematical operation where you take each element of the image, you take each pixel, you add it to its local neighbors, and then it's a weighted sum. So you multiply all the neighbors by these certain weights. So in this example, let's just have this image, x0, x1, etc. And then you have this kernel with what are known as weights. And that's basically how much value I give each pixel. So like W0, W1, W2. So I multiply these, I add these, and I get a new pixel value at the end. Sort of like blurring, actually. The idea is that, like, of a convolution is that, like before we were using like kind of these predetermined kernels. I'm going to pull up the slide again. So like we're using these predetermined kernels, like where it was all the same, or maybe like I weighted the center more. But in this case, for a convolutional neural network, I let the model pick the weights. Like I don't set any weights. The whole point of the training purpose is I slightly change these values of W. And hopefully, the end result is that this filter does this sort of like, essentially it's kind of like, you can think of it as blurring. It's essentially, I take in these raw pixel values, and through this multiplication and multiply add process, I'm able to extract perhaps some useful information from these pixels. And essentially, like when we do this sort of optimization, we're changing these values of W so that we get good results. All right. And so now just how do these networks work? So I have a convolutional neural network basically uses convolutions to automatically extract these features. So links between layers like represent these unique kernels that create these outputs. They're called activation maps. And you pass each activation map through one of these activation functions down here. And activation function is supposed to kind of emulate, like biologically, a human brain's neuron, like either firing or not firing. The point of these activation functions is to add nonlinearity to the model. And you may be asking now, Jeffrey, why is nonlinearity cool? And the whole point is, generally, I want my model represents a mathematical function, and I don't want, if I have this super cool like complex mathematical function, I don't want it to just end up being equivalent to y equals mx plus b. That's not why I made this huge fancy neural network. By adding nonlinearity, I'm able to take advantage of like the full computational power of this neural network. So that way, like the function it represents is like high dimensional and is able to really like take in and like process all this data. Does that make sense? All right. So again, so just revisiting convolutions, there's a few more parameters to defining them. So first is kernel size, which is the dimensions of the sliding window applied to the input. So 3 by 3 is kind of like the minimum kernel size. Just you look at all the neighbors around you. You can also use 5 by 5 if you want to take a look at the neighbors, 2 pixels away from you for some reason. Padding is the next thing. So padding is used when, for instance, you're looking at like the first pixel, like x0. You don't have neighbors above you or to the left of you. So what padding does is I basically make up values for the edge. So a really common scheme is you just use 1. So you just pad it with 1s. So that way it represents like, oh, this is an edge. And like that way it doesn't mess with it too much. Sometimes people use zeros. Sometimes people repeat the edge values. There's plenty of ways to pad. But generally, just padding with 1 is fine. And then the stride is kind of how far along you move your sliding window. So so the default's a stride of 1. So for instance, if I'm looking at x5, I have this convolution centered around it. The next pixel I check is x6. So I just slide over by 1 pixel. So that's my stride of 1. If I jump immediately to x7 in that image, that would be an example of a stride of 2. All right. And other parts of convolutional neural networks, these are less important. If you really want to get into the ML and like just like really understand like how these networks work, definitely read up more about these. But basically, there's fully connected layers, which they're basically they represent matrix multiplications. You just multiply the whole. You basically multiply this big weight matrix, this big array full of weight values with whatever input you have, you add them, you pass them to the next one. So you're not doing any sort of convolution. There's pooling layers. So that's useful when you have like, if you have a really large image, like if you have a 4K quality image, there's no way you want to do all that computation for, all 4,000 pixels, like not 4,000, but there's like a million pixels in there. You don't want to do the computation for each one. And if you're like, if they're similar enough, I can just group them. So pooling, there's different ways to do it. For instance, max pooling is for each like region, you just take them, you just replace it. You just take the max value and you're done. And then there's average pooling where you take the average of all of them in a region and you just have that value. And then batch normalization is a common process used to basically normalize the inputs. So the mean is 0 and the standard deviation is 1 for each neuron. And it's used for to just improve performance. And the idea behind it is like, I don't want like some parts of my model to see, like values of like 1 million and like, like in the millions, and then others are dealing with like really tiny decimals. I want all the values in my network throughout to be pretty similar. So that's the point of normalizing. Is there anything like min pooling where you take the smallest? It could be done. I don't see any reason why not to. Generally, people care about like max and average values though, but I think generally because I think min pooling, you'd usually get just a value of 0. There'd be like some value that's just 0, and 0 is not too useful. So I don't think it's commonly used. I don't know actually off the top of my head if it's a thing, but I don't see why it couldn't be a thing. All right. So now you've essentially had a crash course through what is machine learning, the building blocks of convolutional neural networks. This is like, I'm really speeding through. This is a lot of like, basically, if you understand like all of that, or even most of it, like you're really well equipped to start doing computer vision tasks. Like, and now I just want to just cover some tips and tricks to bring your model performance to the next level if you start working with these models. So the first is the optimizer, which is basically the algorithm that you use to train your model. Basically, what's the process that you take to like kind of move down this hill and find a region where you have a really low error. So here are my favorites. So Adam, if you've done any sort of AI or machine learning in the past, you've definitely heard of it. It's really popular because it's really flexible. Um, you can basically, I never explained what a learning rate is. The learning rate's basically how big of a step you take, essentially. So if you have a larger learning rate, your model will learn faster because you won't be taking like little baby steps. You'll be, taking decent strides. So that way, if you're moving in a good direction, then boom, you're immediately able to go down this hill. The problem with a large learning rate is that for cases if it's too large, you might just step right over you might go from one peak to one peak and you're just going to miss the valley entirely. And you're just going to walk back and forth between those two peaks and you're never going to be able to go down into the valley. So learning rate is one of the things that you just kind of have to like pick. It's more of an art than a science, but Adam is really flexible. Like if you put in like the learning rate, like 1e to the -4, you're probably going to get good results. It's just like, it's super easy. RMS prop is another adaptive learning rate. You can use a smaller one. It's designed to be really stable. I'm not going to go into the like how these work because a lot of math. If you care, you can definitely look these up. There's papers on it. They're pretty dense, but I have a soft spot for a good old standard gradient descent, just the most basic algorithm for moving down, like for training your model. And the reason why is it's tricky to tune because you have to pick things like the learning rate. These sort of adaptive methods, like if you pick a bad value for the learning rate, you can still get away with it. If you do it with gradient descent, so those values are the values for the learning rate. So like 1e to -4 is 0. So 1e to -4 is like 0.0001. So like that's basically like, I guess like the step size. So that's like like how much you're changing your weights like each time. So you're thinking like, you're changing your weights really slowly, but it turns out like that's best. So that way you're like, if you move slowly, you're able to get the best results. If you move really quickly, you might skip over the region where you're doing the best. But for gradient descent, it's tricky to tune. Like if you pick a bad value, it will just screw you over. You're gonna get terrible results. But if you find good values, like it actually ends up having the best like performance for your model overall. If you're new, definitely don't start with SGD. It can give you a lot of pain, but ultimately I have a soft spot for it. Second is data augmentation. Data is everything when it comes to ML. Obviously make the most of what you have. So data augmentation is a way you can essentially make your data set a lot bigger. Like you can take one image and you can make 10 different versions of that image through these sorts of steps. So like for instance, you have this one photo of a cat, you can make 9 different versions of it just from one step, which is like random cropping that's shown here. These steps are pretty straightforward. You can randomly crop to different sections to create like new images. Random flipping, if you flip it over to X or to Y axis, it's a very similar image, but the orientation is different. And it's actually useful for your model to learn, how to deal with these different orientations. And then random rotation, similar deal. You can rotate by a random number of degrees. These steps are useful because, again, like your model is only as good as your data. So if you give a really diverse set of data where your model's seen, like for instance, photos of cats from like every angle, every direction, every lighting condition, then it's ready to, deal with like these sorts of messier photos of cats. Whereas if you just train it on, only photos of cats like profile, at this certain angle, at this certain lighting. The moment you give it a photo that's not at that angle, the model's not going to know what to do. Third is momentum and scheduling. So bad joke at the top. Basically the idea is you don't want to keep your learning rate the same through all like your entire training process. At the beginning, you might want to take bigger steps because you don't want to wait that long. But eventually, once you start to get close, you want to start to move at a slower rate. So that way you're able to get like really into the bottommost part and get the best results. So there's two techniques that are used commonly. I won't go too much into them because like these are worth like 2-hour lectures on their own. But momentum is like, you can think of it as a physics concept. It adds inertia. So basically, when we update a weight, we base it not just on the most current gradient, we base it on the current trajectory as well. So that way, there's less like variation. So for instance, like if I'm going down this hill and there's a little bump in the hill and I hit the bump, I don't want to immediately go, oh no, I need to go in the opposite direction, because I don't need to go in the opposite direction. It's a tiny bump. I'm going the right way. So like the idea of momentum is if I hit a tiny bump, instead of going, oh no, I need to completely switch 180 directions, like I could just look and say, look, I've been going in this direction and getting good, and been improving, for the past, like 100 steps. I'm going to keep going in this direction. And then scheduling is the other thing. So you can modify the learning rate at a predetermined step. So for instance, if if you've trained for a certain amount of time and then you're like, oh, I'm probably getting close to like my model's final performance, I might want to make my learning rate something smaller. So that way I can get better results and I won't like overshoot like these sorts of values. And there's more advancement. That was a lot. So are there any questions so far? All right. And finally, it's just random miscellaneous tricks that are useful. So little things that can make a big difference in your model performance. So the first is, oh, oops, wait, I forgot to update the slide, but I can talk about these. So warm up is basically, so warm up is essentially like this training process where you first kind of like warm up your model on the data. You don't actually modify the model for a bit. You just let it see the data for a bit and get used to it. Dropout is basically a way to make sure that like all the neurons in a neural network are doing, are kind of like pulling their weight. The idea is dropout is like at each training step, you'll randomly like just turn off some of the neurons, like they won't move. So that way, if like one neuron's just carrying the entire network and the other neurons like aren't learning anything, like dropout will like punish that network for like, like the other neurons are slacking, like they need to learn. And then finally, transfer learning. That's basically where you take a pre-trained model, like something that you've trained before in the past. And even if it's on a different data set or something, you've still learned useful features. Like just because, you want to classify pictures of cars, but you have a thing that's trained on photos of cats, right? Like cats and cars both have edges. Cats and cars both have corners. You don't have to start over from scratch. It might not be, the model might not be very good at the beginning, but it's better than starting over. And that's the end of my presentation. That was a lot. I covered everything from classical computer vision to practical deep learning methods and just all the theory behind it as well. You certainly you don't need to have understood everything. So don't freak out if you didn't, because I covered a lot of content. If you actually got all of this or most of it, it is recorded and it will be on YouTube. But if you get like all of it or most of it, this will be like you are very well set to start working on computer vision projects. You like in terms of high schoolers, you could probably consider yourself, I don't know, like probably like the top and like 90% of like high schoolers who do computer vision, like if you understand all of this. So anyhow, I'll just stop for questions for a bit, and then I have a Google Colab notebook where we can start writing some code. I'm just going to drop the link in the chat to that right now. Let me know if you have any issues with it. Questions, comments? All right, I'll still monitor the chat, but I think I'm going to transition now to the Jupyter Notebook. So I'm sorry, the Google Colab. So let's get started. Reconnect. Okay, yes. So is everyone able to view the notebook correctly? Just let me know if anyone has issues like seeing it. You should, in order to run anything, you might need a Google account, but other than that, everything should be self-contained. So I assume you have like some familiarity with Python. If you don't, I'm sorry. It's in Python. Yeah, there's cats up here. There's like there's a little there's a little like notebook setting where you can like have cats appear at the top of your Google Colab, and I love it so much. So it's just there. Don't let the cats distract you though, because we're going to be digging into some computer vision with Python. So there's some basic installs. So you'll need NumPy, which is for scientific computing, and OpenCV, which is this wonderful library for basically all this classical computer vision techniques I discussed in my presentation. Those are all in OpenCV. So you don't have to code, how to do image gradients from scratch, or like, figure out like matrix, like linear algebra on your own. Like use OpenCV, please. So if you just run this cell, it should pip install. I already have it installed, but it should install locally if you don't have these. And I'm just going to start to walk through the notebook. Stop me at any point if you have issues with like running code or like questions or anything. I'll just be monitoring the chat. All right, so we can start with just some basic imports. So we're just importing these libraries. Is everyone able to follow along? Just want to make sure. All right, cool. So if I was running this in a local environment, I'd use an OpenCV function known as imshow, but Google Colab doesn't like that because it opens in a separate window, and like it's janky if you open things in a separate window, like in a browser. So Google Colab has its like own custom version. That's what I'm importing here, and basically, what this code does is if I run this, it will give me a file selection thing, and then I can upload a file. So I can like just choose files. I have a bunch of photos. My desktop is a mess, but I have this photo of a chimp, and I'm just gonna upload that, and it's now been uploaded. So now what we need to do is read that into the Colab notebook itself. I've just uploaded this to like Google Colab's cloud, but it's like not actually in the code. So what I can do is I can use the cv2mread function. And basically I'll use cv2mshow to show it. I've already run this cell before, but if I rerun it, I have this photo of a chimp. You can upload whatever photo you want. It's going to be called like chimp.jpg here. And I say chimp image, but you can upload anything you want. Let me know if you have any trouble with any of this. Is everyone able to upload an image and get it to show correctly? Could someone just, if so, just drop yes in the chat. If not, let me know like what issues. You can feel free to unmute or anything. Just let me know how you are doing in terms of following along. All right, nice. Fair enough. Got to pick a nice image. All right, I'll just maybe the file need to be called. Oh yeah, yeah. You have to rename it, or you can just change the code in here. cv2mread. Just call it the essentially the name of like whatever file name you uploaded. You can just change it here. So like whatever. So that way it can you'll be reading the right image. All right, I'm gonna be moving on. I hope I'm not moving too quickly. Just let me know if like I am, and I'll slow down. So we can start with, so let's just start with a color space conversion. So CV2 has this convert color function, that you can convert the color space of an image. So for this case, we'll actually not be using color channel data. A lot of OpenCV functions actually only accept grayscale images. So usually a safe first step is just converting to grayscale. And when you're doing a classical computer vision task, because generally like you don't need colors. You mainly care about things like edges and corners. So you can save a lot of space that way too, because you're throwing out, like the orange and like instead of like RGB, you just have like intensity value. Minor tidbit is that OpenCV reads in images as BGR, not RGB, so blue is the first channel. Keep that in mind. It won't affect this notebook. If you work only in OpenCV, it won't affect you as well. Oh, Edward, are you asking about BGR? Why would you do that? The answer is I don't know. The developers of this did BGR. I hate it sometimes too. If you work with like 2 image processing libraries in Python, like you'll run into weird things because like one's BGR and one's RGB. Like I've had cases where like I'm trying to like display a photo of I think like a person or something, and they're just colored blue because I forgot that OpenCV is BGR. So then like it displays and I'm like, what's going on? And then I realized like, oh, the colors are flipped. So janky thing to deal with, but you just have to keep that in mind. So you can run this, and then if you run CV2mshow, you see you have a gray image now. Very solid. So you guys are like probably like Jeffrey, you just made an image grayscale. OpenCV scam. It's not that cool. But now let's get into some more cool stuff. So now we can start with image preprocessing. So let's start with trying to blur an image. So there's a CV2 Gaussian blur function, which is used for blurring. There's plenty of blurring methods. I show another one down here called median blur. So that just blurs based on the median of like the like kernel region. And I take in this grayscale image, and then this is the kernel size. So median only takes in square ones. So I just put in 5. So it's a 5 by 5. And then for Gaussian blur, it can be any rectangular thing. So I do a 5 by 3. And then the other value it requires is the standard deviation in the x direction. You can just leave this as 0 generally. It won't affect it too much. So you can run this, and then you can run imshow, and you can see that I don't know if you can tell, but I think you can tell that these images have been indeed blurred compared to the original image. And you can mess around with these parameters. So if I make this a really large kernel size, I think you might be able to see the blur more noticeably. Yeah, you can see the blur more noticeably. So that's blurring. Oh yeah. Yeah, Leo, you do not have to write all this code yourself in C. OpenCV actually also has, they also have a C library. I think the code's originally all in C. So you do not have to write it all from scratch. Please do not write computer vision things from scratch. OpenCV is a lifesaver. Okay, what's the difference between Gaussian and median blur? So Gaussian blur blurs using a Gaussian kernel. So I don't have my slides, but I'm gonna like quickly. I'm gonna like. I can't draw this, but like the Gaussian blur basically uses a Gaussian kernel, so it weights elements that are like closer to the original pixel, like more than pixels that are further away. A median blur basically it just what it does is it simply takes the median value in the neighborhood region and just sets the pixel values all to that. Does that make sense, Dolphin? Okay, cool. So it's like a different blurring function. Like functionally, the blurs are really similar. Generally, people just use Gaussian blur, but it's good to know that there's other ones out here. So next, I'll just demonstrate 3 types of thresholding. I have a lot of reading here about like the specific arguments if you want to play around with it. But basically, there's 2. I show there's 3 types of thresholding, and 2 are not adaptive, which means that the same threshold is used across the entire image. So it's a global threshold. What that means is like the threshold value that I set will just be applied across the entire image. And an adaptive threshold, that's if you want to threshold in like a smarter way. Like if you have an image with a lot of contrast, right? Maybe I don't want to use the same pixel value because otherwise, in one region it might work really well. In the other region, it just might all like fade to black or something, and that's not useful. So I demonstrate there's 3 types of thresholding here. So in this code snippet, so the first one is global thresholding. So that's simply, so I just pass in the image that I blurred Gaussian. And then the second argument is the threshold. So in this value, it's 127. So any pixel value above 127 in the image, I set it to 255. Anything under, I set it to 0. And then 255, this is just like the maximum pixel value. You just always set it to 255 because that's the maximum pixel value. And then I specify this is a binary threshold. So I'm telling OpenCV, I only want the values in this image to be 0 or 255. That's it. Next is Otsu thresholding. So that's basically like the Otsu algorithm. I brought it up. It showed up on a slide, but the way it does it is it basically automatically computes the best threshold value to use. It does that using some statistics and histograms and stuff. But basically, what you have to do is you just add plus EV2 thresh Otsu here. So it's a binary threshold, but I'm using the Otsu algorithm. So whatever I pass into this like threshold like value like doesn't matter because I'm automatically computing it. Like so I just passed in 0. And then this is an adaptive threshold. So an adaptive threshold, it's Gaussian again. So what this means is I take like small neighborhood regions in each image, and I apply Gaussian kernel over it. And based on that Gaussian kernel, I compute a different threshold for each like region. So the arguments I pass in the original image, Gaussian maximum pixel value is 255. I specify this is an adaptive Gaussian threshold. It's a binary threshold as well. And then this 11 is the neighborhood size. So for each 11 by 11 neighborhood, I'm going to compute a different threshold. And in this value of 2, it's just used in the threshold computation. It's a constant. Like this stuff doesn't matter too much. You can just leave it. So I'm going to run this, and then I'm going to run imshow. So as you can see, we get 2 like thresholded images. Like you can notice there's some difference like in the feet here where there's like these different splotches, and that's where you see the difference between my like manually set threshold and then my Otsu threshold. My Otsu threshold is able to get these splotches. So it's just like minor differences like that. But the adaptive threshold is where you really see the difference. So in these ones, because I'm using the same threshold across, for these like sort of dark like fur regions on the arms, these just all become black when I use a global threshold. So I lose all the edges and all the details in these areas. I get the outside outline perfectly fine, but I lose like this entire arm, like it's just gone. I see like the chimp's hand, the arm's gone. But with an adaptive threshold, you're able to make out these edges, and you're still able to keep this detailing because I'm using a different threshold for each region. Does that make sense? And is everyone following along okay? All right, cool. And then finally, you can create gradient images using the CVT Sobel method. So Leo was talking about how he's painfully writing gradient image computations by himself. Please don't do that. CV2 will literally do it for you. So in this example, what we do is we basically take for the CV2 Sobel function, it takes in an input image. Ddepth is basically kind of the depth of the output image. It's like the numeric type that you use. You can just use like float 32. Just leave it like that. That's generally like a good. You can just pretty much always leave this, and then you have dx dy. Dx like these you either set to 1 or 0. So dx specifies like it's the order of the derivative in the x direction. Dy is the order of the derivative in the y direction. So we don't care. We generally if you take in some calculus, like you know what orders are. Otherwise, don't worry about it. For our purposes, we'll be using the first derivative because that's like the direction of change. Second derivative is something different, but basically just leave it as one. And then k size is just the kernel size. So again, like how big of a neighborhood we're using for each of the computations. So we first create an x gradient image using this function call, and then we create a y gradient image using this function call. And then to get the combined gradient image, what I can do is use the CV2 add weighted function, where I assign these two images equal weight, 0.5, 0.5, and then I can basically add them together. So you can like merge photos really easily this way. And then I can run this. If I run this, you see you have a nice gradient image. You can see these lines all represent like these directions of change, which oftentimes are like these sorts of edges. So as you see, you can get this really cool gradient image with all this detailing here on the fur. You even get like the like JPEG, you even get like the PNG like squares. You can see like these sort of wavy lines here, which is kind of cool. So yeah, any questions about that? All right, if not, I'm gonna move on to feature detection. So we've learned how to pre-process images, and now we can just start with the two feature detection things we learned, which was edge detection and then corner detection. So the main function we talked about was canny. So it's CV2 canny. It's a really easy function call. You pass in the input image, and then all you have to set are your threshold values. So remember I talked about weak and strong threshold values. So this is, so I can set like different min and max values. So I can run this, and then I can get an output edge image where where you can see like all the edges within the image. So now we can play around with this a bit. So you guys can experiment on your own, but just put into chat, what do you guys want to suggest for a minimum weak threshold value? 0. All right. So basically, there's no such thing as a weak threshold. Everything is like, I'm not throwing away any pixels. What happens? Not too much changed, but I think if we see the difference, I think you can see that some of these edges will be a bit wider because I'm not suppressing those pixels. But again, it's pretty similar. A more noticeable change might be if I lower the threshold. If I lower it from 150 to say like 50, you see like there's now a lot more detailing. Before I didn't have like these sorts of wrinkles on the face. And that's because I'm defining these to, I'm including these pixel values in the edge calculation. And if we look at the original image, like these features are definitely more subtle. And like it's like this dark gray to like this gray compared to like, black to white. So it makes sense that those values are less intense compared to like these edges. So that way, when I increase the threshold and say I only want really strong edges, you see like some of these wrinkles end up disappearing. It does make the chimp look older. All right. Is everyone able to follow along? All right, cool. Now I'm going to move on to Harris corners. So there's a built-in method again, and there's 4 arguments. So there's the input image, the block size, which is how big of a neighborhood you use for corner detection, and then the kernel size, which is how big of a neighborhood size you use for computing the gradient image. Remember, we first apply the Sobel derivative, so we get this gradient image first as the first step for corner detection. So this value of 3 is for the kernel for that. And then there's this value of k, which is the Harris detector free parameter. It's another constant in the algorithm. Honestly, like I don't know off the top of my head, like specifically what this does. But generally these values will work pretty well. Like 0.04 will work pretty well. Like honestly, like all these values work pretty well. Like um, full disclosure, I like copied and pasted this from one of my previous projects. I didn't like tune this at all on the images. And if I run this, I get you get pretty decent like corner detection. So these are generally good parameters. You can play around with these a bit. Like maybe if I increase the size significantly, you see like the points are a lot larger now. Like for the neighborhood size, you see like instead of these like smaller dots, there's a lot more points bunched up. So you can see how like changing these parameters might affect your corner detection. Generally, this is something that you'll have to tune manually though, in your projects. So if you're working with like an example set of images, if you're not getting good results, you oftentimes have to play around with these parameters until you get something good. And then you hope when you apply this into your application that these parameters will work well for all the images that you get. So this is the function call. The CV2 dilate just makes these images these pixel points slightly bigger. And then this just sets all the pixel values to red. So that way we can make out the points. And if y'all want, you can play around with the parameters, go wild. Like what if I make this 10? You see like there's some changes, not that like some mild changes, I guess. But yeah, with computer vision, you'll get 1e. We could try 1e to -4. It's the learning rate I use, but it's not. I think we see like a lot smaller points here. Like for instance, you get these like really small points over here. They're less bunched. But yeah, definitely like look into these parameters. If you want to tune these, generally mess around with like the block size and kernel size. I don't remember what these constants even do. So like generally, like know what you're playing around with, and like don't just like blindly mess around with values. Kind of have kind of sense for what you want to do, right? Like if you're realizing like, oh, I'm not getting enough corners, then maybe you want to increase the neighborhood size or something like that. Is everyone following along? Everything makes sense? All right, cool. So now I'm going to get into the fun part. Image recognition with TensorFlow. So we've gone over classical methods now. So now let's look, we're gonna, in the time that we have left, I'm gonna try to build a simple image classifier. So I hope I'm not been going too fast. So just stop me. Like, is my current pace fine? Too fast, or is there anything that you guys want to review? Just looking at what's in the chat. All right. Okay. So again, there's a TLDR blurb again of just like how do ML models learn over here, and then let's get right into like creating these models. So I'm gonna start first with just installs. So if you run this line, this should. I honestly don't remember off the top of my head if pip install does dependencies automatically, so I included some, but this is basically all you should need. And I already have all the requirements, but it might take a bit longer for you guys. And also let me know if you have any problems with this install. So I can help with that. And if you want to check your installation, you can just run the below lines. This basically imports TensorFlow. I create like two tensors, which are basically basically like matrices and TensorFlow. And then I multiply them together and I print the result. Let me know if I need to pause to wait for installs or anything. Okay, no one said anything in the chat, so I'm just gonna move on. So we can get into the actual machine learning now. So we're gonna create model on the MNIST data set, which is basically it consists of handwritten digits from 0 to 9, and the goal is to recognize these handwritten digits. So we can basically, there's this big code snippet here. Well, basically we do these imports. This is just a helper function to just help us visualize the digits. You don't need to worry about that. So this first line here, what I do is I just I just create this variable MNIST and I define this is the data set, so tf.chars datasets MNIST. And then I can simply call load data on it, and I will immediately have the train images and the train labels, and then test images and the test labels. So train images are what you would use to kind of train your model on, and that's what your model is going to be learning on. And test images are the images that you don't learn from, but you just evaluate your model's performance on. Don't train on the test images, because the whole point is it's supposed to be images that your model's never seen before to see, is your model just memorizing the data set, or is it actually learning things? And then the labels are just, you can think of them as the answers. So what the digit actually is. This is just a reshape operation. Basically, TensorFlow expects images to be kind of have 3 dimensions. They expect, width, height, and then RGB. So so it expects 3 here. These images are grayscale, so that's why it's 1. And we can just simply do that using np expand dims, and then we add an extra dimension to the last kind of the last dimension. So before it's 28 by 28, then I add in -1 in Python, it's the last one. So I add an extra dimension there. And I do that for train images and test images, and I can visualize it. And then this last step over here is generally machine learning models prefer values in the 0 to 1 range. There's some theoretical machine learning that behind why this works and why this is, but generally it's a good rule of thumb. So what we're going to do here is divide all the pixel values by 255. So that way all the values are between 0 and 1. And if I run this, it might take a while to download the data set. And now you see there's these example images from the data set. So you see these are all handwritten digits, and our goal is to be able to recognize them. That was a lot of code, so I'm just going to stop for a bit. Does anyone want me to go over anything, or is anyone having trouble with running anything? Oh, the -1 basically, originally the images are 28 by 28, right? But TensorFlow expects basically this extra, so this is this is 2-dimensional, but TensorFlow expects images to be 3-dimensional. So this -1 basically says I'm going to add an extra dimension, right? Expand dims, and this argument, so this is what I'm adding it to, and then this is what index to add it to. So if I put in 0, this this extra dimension would be here. If I put in 1, this extra dimension would be here. I want it to be in the last dimension, so I just set -1, because in Python -1 automatically goes to the last element in a list or in a thing. So I just set -1 to add this 1 dimension last. Does that make sense? Okay. Yeah. Anyone else have any other questions? I also realized I think this workshop was scheduled to be around 90 minutes, but I have a bit more content. So if you have to go, feel free to, but at the same time, we can work through this example as well. And if you have time, I think it's cool to just learn how to create your own ML models. So feel free to stick around. If you have to go though, no worries. So now what we can do is we can define our ML model. So we'll be using convolutional and linear layers. So those are fully connected layers, like those big matrix multiplication things that I had in my presentation. And we're using convolutions because they work really well with image data. So in Keras, what you can do is you use the sequential wrapper. So it's tf.keras.sequential. And then what you do is you can pass in a big list of layers. And then what sequential does, it'll take all these layers and then it'll make a model out of them. So what that does is that's how like you kind of construct the model. So I have like these convolutional layers here, conv2d, conv2d. I set a kernel size of 3. Filters is basically the number of like outputs from like after this specific layer. These values matter, like don't mess around with them. Kernel size you can change. If you mess around with these, like there'll be like the wrong number of outputs for the next layer. So like these are all like dependent on each other. All of these values for the filters are dependent on each other. Kernel size though, you can feel free to play around with. Flatten basically takes my two-dimensional, like basically my convolutions extract these like two-dimensional features from my image. And then what flatten basically I like think about it like I unroll this two-dimensional image into just like this long list of numbers. And then I can pass it through these these linear layers to do my final computation. And note that at the end, I have this value of 10. So that what this is going to be outputting is probabilities for each of my 10 classes. So like basically this will give a list of like 10 probabilities. Like the first thing will be the probability that this is a 0, the probability that this is a 1. Shape for a model. So firstly, that's somewhat dependent on the input, which is, in this case, it's 28 by 28. If you want to make your own models, like playing around with the shape is like, it's kind of dependent on like what you want to do. There's like a lot of research that goes into this, and generally, actually don't recommend you build your own models from scratch, because it's like deciding shape and things like this is not like super trivial. And like there's people who have done this work before. There's researchers that have gone and figured out like, oh, these sorts of model architectures work really well for image classification. So in practice, don't build your models from scratch. Like use stand on the shoulders of giants, right? So but essentially like deciding on the specific shape, it depends on like what you want to do. For instance, like if you might want more filters, but if you want to, for instance, extract more information from a certain thing, but then you might have to change your kernel size. It's somewhat complicated to figure out the specific shape, but and also like what specific layers as well. Like how many conv layers do I use? Like I could keep throwing these in. Generally, like yeah, there's also ML tools to find like shape and settings and things like that. Generally, like deeper networks are better. I don't want to. That's a very big generalization. Like kind of intuitively, like the more layers you have, the more like computational like flexibility you have, and thus like you're gonna perform better. That's not always true though. Anyway, like model architecture is like people dedicate their lives to doing it. So like you can get really sucked into this. But I think it's good to understand conceptually like how to put together things, but in practice, if you're deploying ML models, you'll very rarely be making your models from scratch. Anyhow, did that make sense? Cool. So now what we can do is we can begin training our model. So we have 2 hyperparameters here. So again, these are values that you just have to pick. Like these are like specific values that define how your model trains. Your model doesn't learn them. So these are the things that you really have to tune. So we have a learning rate here. I'm just going to start running this because this will take a while to run. So this has started training, as you can see. So we have the learning rate. So I set it to 0.01, and then we have momentum. So that's something I brought up. I'm adding momentum. So that way I'm able to continue in a certain direction, even if I hit like small bumps. And then for my optimizer, you can play around with this. There's plenty of optimizers you can use. Not all of these take these arguments, but something you might want to try is tf.keras optimizers. Atom obviously is a really popular one. So you could potentially like try this, like switch out this line if you want to see the difference. And then there's this model called compile line. It's basically I'm combining my original model with the optimizer, and then I define a loss function. I'm not going to get into like the specifics of the loss function, but this basically computes like how off my probability values are from like when I'm predicting like the class when I'm classifying images, like how off I am. And then metrics accuracy, because I want to track the accuracy of my model. And then I call model.fit to basically fit my model to this training data. So I have train images, train labels, epochs. An epoch is basically one like pass over the training set. Generally, you want to train for a few epochs, definitely not just one. Since this is a really simple data set, and you can see my accuracy is already pretty good, I'm just going to do one, and also for time's sake. But generally, you want to train for more. And then after I finish training, over here, I can simply call model.evaluate on my test images and my test labels. Verbose is basically how much output it gives, and it will tell me, according to my loss function, like how much error I have, and it'll also tell me the accuracy, which is like the figure everyone cares about. So while this runs, is there? Oh, nice. Y'all have faster computers than me. Does anyone have any questions or things I want to review while this thing sits and chills? If y'all finished running this, something else you can play with is play around with learning rate. What happens if you make it really big? Like make Collab does run the code on your local machine. You can pick the runtime actually. You can check. So hardware accelerator right now it's none. So it's just running on my local computer. I believe, maybe. I actually don't know where it runs. But you can also accelerate. So GPU, TPU. They actually provide it for free, which is really nice. So like if you're doing like machine learning and stuff, and you need to like, because like GPU acceleration can, yeah, it might run on their machines. I might be wrong on that one, but yeah, you can pick like to use GPU or TPU acceleration. You have to write a bit more code to do it, but it will speed up your training like tenfold or more. So if you want to get into machine learning for something really useful, I think finished 93% accuracy. Sad. I got better performance when I previously ran this, but anyhow. So that wasn't. So did that make sense, everyone? Oh yeah, Edward. Yeah, you can choose local, I guess. Hosted or local runtimes. Any questions? All right, then I'm gonna keep moving forward. So this is a really simple data set. Like MNIST is like 60,000 images, which sounds like a lot, but ImageNet, which is like the main one that a lot of researchers work on, is like it's 1.6 million images. They're a lot bigger, and you're using much larger models. So if you're training models from scratch, it takes hours, days, sometimes weeks to train state-of-the-art models. And for your learnathon, obviously you don't have a spare 2 weeks sitting around where you can just kind of sit and destroy your computer. So, oh yeah, quantum machine learning is there's a lot of potential there. I haven't looked into it too much, but potentially there's improvement there. Right now, like yeah, even with GPUs and like serious like hardware, it can take a really long time to train, and that's just the nature of like how state-of-the-art models are now, because they're really big. Like I don't know if you guys have heard of GPT-3. It's like all the rage now. It's OpenAI's new natural language processing AI, but that it was trained on like a trillion like files, like, and like it has like billions of parameters. So like for instance, I can actually there's this nice function. I'm just gonna quickly open up. If you run model.summary, it'll give you like kind of like this output of like what your model is. So it'll tell you like the output shapes and then like the number of parameters. So like this is like 4 million parameters. It took like 3 minutes to train on just like one epoch. If you're talking about like these models with billions and billions of parameters, it takes a really long time to train. So then the questions, like how to use ML. Like if I'm spending all my time waiting for things to train, it's not very useful. Fortunately, there's a platform called TensorFlow Hub where developers have already published a lot of their pre-trained models on different tasks. And simply, you can utilize those pre-trained models with just a few lines of code, and you can quickly download it and integrate it with your application. So we're going to be doing a real image classification here, not digits. And we're going to be using the MobileNet v2 model, which is one of the most popular, efficient image classifiers. Like it's efficient enough to run on your phone. So if you want to create a mobile app and use ML, MobileNet's a really great choice. So you should have already had TensorFlow Hub installed in the previous pip install line. So there's just a bunch of imports here. And you can provide, there's the URL to the model on TensorFlow Hub here. If you want to check out their other models, you can just go onto TensorFlow Hub, check out their what they have published there. And then here I set the image shape. MobileNet just like, it's predetermined, and MobileNet takes in 224 by 224 images. And similar thing to the -1 thing here, what this line does is basically I pass the input shape as 224, 224 by 3, because I'm using color images now, so RGB. And again, you see there's this tf.keras.sequential to define my model, but I only need to pass in one thing now. I just pass in hub.keras layer, and then I pass in this URL to this pre-trained model. I set the input shape, I run this, my model's done. Nothing else to it. I don't have to define anything else. Easy, done. And now I can test on an example image. So I can download this example image from Google, and like I can open it and then just visualize it here. So it's Grace Hopper. And down here, what I can do is, again, we need to first normalize this image to the 0 to 1 range. That's why I'm dividing by 255. And then I simply call classifier.predict on this image. There's also this new access call. This is because this classifier actually expects like a 4-dimensional input. It's because usually you pass in like lots of images. You don't just pass in one image. So like this would be like the number of images you're passing in, width, height, like RGB channels. So what this new access does is it basically adds this extra 1 dimension here. And then I can call classifier.predict, and I get this result. And this is a list of probabilities. So what I do is I take NP argmax basically takes the largest, the index of the maximum values along an axis. So what this does is I just take the index that has the greatest probability, and that's what it's predicted as. And then obviously that's just a number though. It's not like an actual like, what the thing is. So we're going to download this labels path for like what indexes correspond with which labels. And then we can visualize the results. And I'm going to run this, and prediction military uniform, solid. No training, like 50 lines of code maybe. Did it in like 5 minutes. State of the art image classification right here. So all in all, TensorFlow Hub is a really great way to get started with machine learning, because you don't have to do any of the training. You can apply these sorts of, you can directly apply it to your application. And if you want, you can actually like retrain these. So you can actually build upon these. For instance, what you can do is, I don't have it in this notebook, but what you can do is if you define like the classifier using this pre-trained model, you can add more layers if you want, and like you can customize like these pre-trained models to your desire. You can retrain them. You can do all sorts of things with them. So that's an amazing way to just get started with computer vision and machine learning, which actually segues sort of into the challenge for today's workshop, which is just build an application that uses TensorFlow Hub in some way, just using pre-trained models. Build upon like the pre-trained models provided. On TensorFlow Hub, you can go on the website, look for anything you desire. They have things from like natural language processing to image classification, all kinds of cool things and just apply one of those models to like a computer vision task. And yeah, so that's the end of the workshop, the slides, and the notebook. So yeah, are there any final questions? And questions, comments, any of this? I can, I think I've already dropped the collab link. I can send it again, just in case anyone wants to keep this around. And yeah, now's the time for questions. So. All right. So if there's no more questions, I think we're at a close. I might hang around for a little bit. So if you want to hang around and just like ask me anything, I'm totally cool for that. Otherwise, yeah, feel free to go. And thank you everyone for attending. I hope you learned a lot. Hopefully you aren't too intimidated by all the content that we covered today. It's certainly a lot, but if you got even half of it, I think you're very well equipped to understand and talk about computer vision and start using it in your applications. What's up, Nathan?
That was an accident.
Oh, you're good.
I'll end the recording.